Welcome back. How are you feeling today? I hope you're feeling good and alert because we're about to embark on the most demanding calculation in this course. It involves calculus, lots of it, far more than we'll use anywhere else. Those of you who love calculus are rejoicing right now. Others, maybe not so much. And if that's you, just hang in there. Absorb what you can. I'll try to make it rewarding, even if you can't follow every single step. Our goal is to understand the relationship between Kepler's laws of planetary motion and Newton's laws of gravity and motion. Last time we showed that Kepler's second law follows from the conservation of angular momentum. And we derived Kepler's third law, at least for the case of a circular orbit, starting from F equals ma and the inverse square law of gravity. That brings us to the main event, Kepler's first law. The planets move on elliptical orbits with the Sun at one focus. For this one, we're going to take a different tack. We're not going to derive it from Newton's laws, although later I'll show you how to do that. Instead, we'll go the other way around. We'll put ourselves in Newton's shoes and let Kepler's laws inspire us to discover the inverse square law of gravity. So, imagine, the year is 1660, the law of gravity is unknown. We've just read Johannes Kepler's books and puzzled over those three patterns he observed in the motion of the planets. Can we use those patterns to figure out the law of gravity? This is a tough problem. It took Newton years to solve it, and we have 30 minutes. But we have an advantage. We know calculus. Newton had to invent calculus, which naturally took some time. So we won't follow Newton's historical path. We'll take a more efficient route. First, let's write Kepler's laws in equation form. The first law says the orbits are ellipses with the Sun at one focus. So if we use a polar coordinate system with the Sun at the origin, the path of the planet, r of theta, is equal to a times 1 minus e squared over 1 plus e cos theta. That's the equation for an ellipse that we derived last time in terms of the semi-major axis, a, and the eccentricity, e. Kepler's second law says that the line from the Sun to the planet sweeps out area at a steady rate. Last time we showed that this implies 1/2 r squared d theta dt is a constant, a certain area per unit time that's specific to each planet. For the Earth, the numerical value is pi au squared per year, since the Earth's orbit is approximately a circle of radius 1, which has a total area of pi. More generally, 1/2 r squared d theta dt is equal to the area of the ellipse, pi a squared times the square root of 1 minus e squared, divided by the orbital period, p. That's Kepler's second law. And Kepler's third law. It says that p is proportional to a to the 3/2 power. So that's our trio of equations. Now let's get to work. Pretend we already know from laboratory experiments that force equals mass times acceleration, but we don't yet know the equation for the force of gravity. To obtain a clue, we need to calculate the acceleration of a planet that obeys Kepler's laws. To calculate acceleration, first we need to know the planet's position as a function of time. Then we'll take the time derivative to get the velocity. Then we'll take another time derivative to get the acceleration. Well, Kepler's first law tells us the position, but not as a function of time. It's as a function of angle, theta. All of the time information is in the second and the third laws. So we need to combine the equations somehow. Another problem. We wrote Kepler's first law in polar coordinates. But with vectors, like acceleration, it's much easier to take derivatives in Cartesian coordinates, x and y. So let's convert to Cartesian coordinates. In general, when the polar coordinates are r and theta, the x-coordinate is r times the cosine of theta, and y equals r sine theta. So for our planet, x is a times 1 minus e squared times cos theta over 1 plus e cos theta. And we get a similar equation for y. We can do the same thing with unit vectors. In the polar coordinate system, r hat is a vector of length 1 pointing in the direction of increasing r. That means r hat changes orientation as the planet moves around. It always points away from the origin. At any point, though, we can write r hat as x hat cos theta plus y hat sine theta. File away that equation. We'll need it later. Now, let's calculate the velocity by taking the time derivatives of x and y. Since they're written as functions of theta and not time, we need to use the chain rule. Vx, the x component of the velocity, is dx dt, which we can write as dx d theta times d theta dt. And to get dx d theta, we use standard tools of calculus. Since x has functions of theta in the top and the bottom of the expression, we use the quotient rule. We take the derivative of the top times the bottom, minus the top times the derivative of the bottom, divided by the bottom squared. And we can simplify a bit. What about d theta dt? For that, we need Kepler's second and third laws, the ones relating to time. Let's consolidate them by writing the p in the second law in terms of a using the third law. The third law says p equals some constant times a to the 3/2 power. We can label that constant however we want. Maybe we should just call it k. But instead, let's be clever. The second law has a 1/2 on the left side and a pi and a square root on the right side. So to make the result as simple as possible, let's write the third law as p equals 2 pi over root k times a to the 3/2, where k is a constant. That way, the 1/2 and the pi cancel out, and the k will fit nicely under the square root. So what we're left with is r squared d theta dt is equal to the square root of ka times 1 minus e squared, which we can use to solve for d theta dt. Now we have the ingredients we need to calculate velocity. Vx is dx d theta times d theta dt. We plug in the expressions we just derived, which leads to an equation in terms of r and theta. To put everything in terms of just one variable, theta, we insert the ellipse equation for r of theta, and then simplify. That gives Vx is equal to minus the square root of k over a times 1 minus e squared times sine theta. That factor in front of sine theta, it's a constant. It doesn't depend on r or theta or time, and it has units of velocity. So to make the equation look even simpler, let's just name that constant v0. That way Vx is simply minus v0 times sine theta. That leaves the other component of velocity, Vy, which we can calculate as dy d theta times d theta dt. The steps are very similar to the ones we just went through for Vx, so I won't use our precious time together to spell out the details. I'll just jump to the answer. Vy is equal to v0 cos theta plus v0 times e. What does all this mean? Let's find out by tracking the planet's velocity vector over a full orbit. We'll plot Vx on the horizontal axis and Vy on the vertical axis. That kind of chart is called velocity space. Each point in the chart specifies a velocity rather than a position. As theta increases, the equations tell us that Vx starts at 0 and Vy starts at v0 plus e. Then as theta increases, Vx goes negative and Vy shrinks. And when we keep going, what we find is amazing. The tip of the velocity vector moves in a circle. You can prove it algebraically, too, by showing that our equations imply Vx squared plus Vy minus e, V naught quantity squared, equals V naught squared. And that's the equation for a circle in velocity space with a radius of V naught and a center at the point 0, e times V naught. Now this is ironic. Ancient astronomers were sure that the planets moved in circles because the circle was just such a perfect shape. And when the data got good enough to rule out uniform circular motion, they added more circles to make epicycles, and it took astronomers a long time to ditch the circles and arrive at the truth: the planets move on ellipses. But look what we just found. The ancient astronomers were right after all. Planetary motion does involve perfect circles. It's just the circles are in velocity space. While the planet moves in an ellipse, its velocity vector traces out a circle. Well, that was an unexpected treat. But remember, our original goal was to work out the acceleration. So far we have velocity, so we need to take another time derivative. The x component of acceleration, ax, is dvx dt, which as before we can use the chain rule to write as dvx d theta times d theta dt. The theta derivative is simply minus v naught times cos theta. And remember, v naught was our shorthand for the square root of k divided by a times 1 minus e squared. And d theta dt is the square root of k times a times 1 minus e squared divided by r squared. So there's a nice cancellation, leading to minus k over r squared times the cosine of theta. The y component works the same way. We take the theta derivative to get sine theta, then plug in d theta dt, leading to minus k over r squared times sine of theta. So in vector notation, we just learned that the acceleration is minus k over r squared times x hat cos theta plus y hat sine theta. And hey, wait a minute. That combination of unit vectors is none other than r hat, remember? So what we've just shown is that acceleration is minus k over r squared times r hat. Eureka! It all hangs together. We can explain Kepler's laws if we assume the sun is pulling on the planet with a force whose strength varies as 1 over r squared. We've just discovered the law of gravity by following Kepler's 3 clues. And that constant that appeared in Kepler's third law, we now see it sets the overall strength of the sun's gravitational force. If we are willing to further assume that the force is proportional to the mass of the attracting body, we can write k as g times m sun, where g is a fundamental constant of nature. Try to imagine how exciting that would have been, to be the first person to reveal the first of the 4 fundamental forces of nature. But now let's return to a more modern stance in which we already know the law of gravity, and we want to understand some other aspects of planetary motion. Specifically, let's think about the 2 big conservation laws, the conservation of angular momentum, L, and energy, E. Both L and E remain constant throughout a planet's elliptical orbit, even while the planet is moving and changing speed. So we should be able to derive expressions for L and E purely in terms of constants, G, big M, little m, A, and E. First, let's do that for angular momentum. In general, L equals m times r times v theta. Remember, only the angular component of the velocity matters. And since v theta equals r d theta dt, we can also write L as m r squared d theta dt. And earlier in this lecture, we consolidated Kepler's second and third laws into one equation. R squared d theta dt equals the square root of Ka times 1 minus e squared. If we multiply this by little m and substitute gm for k, we arrive at a new formula for angular momentum. Little m times the square root of g times big M times a times 1 minus e squared, which is purely in terms of constants, as advertised. As an immediate application of this formula, we can take care of a piece of unfinished business, Kepler's third law. Last time we proved it for a circular orbit, and now we can prove it for the general case of an elliptical orbit. We start with Kepler's second law. 1/2 r squared d theta dt equals pi a squared times the square root of 1 minus e squared, that's the area of the ellipse, divided by p, the orbital period. Notice, the left side of this equation is the angular momentum L divided by 2m. Now let's use our nifty new formula for L. When we insert that, the little m's cancel out, as do the 1 minus e squareds, and if we solve for p, we find that it's 2 pi over the square root of g times big M times a to the 3/2, which is, of course, Kepler's third law. Thus endeth the proof. So that's enough playing around with angular momentum. How about energy, the other conserved quantity? Energy has two parts: kinetic, 1/2 v squared, 1/2 mv squared, and potential, minus g times big M times little m over r. Their sum must be equal to some combination of the constants g, big M, little m, a, and e. And let's try to figure out what it is. Since energy is constant, we can calculate it at any point we want in the planet's orbit, and we'll get the same answer. So let's make life simple by choosing theta equals 0. That's when the planet makes its closest approach to the sun, and r equals a times 1 minus e. What about the velocity? Well, we can figure that out with another application of our new angular momentum formula. In general, L is equal to m times r times v theta. Here at theta equals 0, v theta is simply v, because at that point the velocity vector is totally perpendicular to the radius vector. R is in the x direction, and v is in the y direction. So at theta equals 0, L equals m times a times 1 minus e times v. We solve for v and plug in our new expression for L. Then we insert that expression for v into the energy equation and we simplify. The algebra leads to a cascade of cancellations and a result that's refreshingly simple. The energy is minus g times the product of the masses divided by 2a. All the terms related to eccentricity ended up canceling out. It turns out that energy depends only on the semi-major axis of the ellipse and not its eccentricity. If you have a nearly circular orbit with a radius of 1 AU like the Earth, and you compare it to a planet on a highly elliptical orbit with a equals 1 AU and an eccentricity of 0.9, they both have the same energy. They also have the same orbital period, 1 year, because Kepler's third law says P depends on A, but not on E. The planet on the elliptical orbit whips around the sun nearest closest approach and moves more slowly when it's far away, and the two effects cancel each other exactly to give the same period as the Earth. It's an interesting coincidence. I hope you'll agree. We've accomplished a lot in this lecture so far. We showed that Kepler's laws imply an inward acceleration varying as 1 over r squared. Then we derived handy expressions for the angular momentum and the energy associated with a gravitational orbit. This involved a lot of derivatives and algebra. But some of you might be more visual thinkers, so I want to show you a graphical way to understand orbits. I think you'll find this technique leads to a greater understanding, and it'll also be useful when we explore other areas of gravitational dynamics, like black holes or the expansion of the universe. So, imagine a particle of mass little m that's gravitationally attracted to a larger mass, big M. We give that particle some initial position and velocity, which in turn corresponds to some value of the angular momentum and of the energy. As before, the energy is 1/2 mv squared minus gmm over r, and the v squared has two components, radial and angular, vr squared and v theta squared. Let's now bring in the conservation of angular momentum. L equals mr v theta, so v theta equals L over mr. That allows us to rewrite the energy equation as E equals 1/2 mvr squared plus L squared over 2mr squared minus gmm over r. Now that's an interesting way to write it, because the second term is purely a function of r. That makes it look like a sort of potential energy, even though it's really part of the kinetic energy. And that's the basis of a neat trick. We define an effective potential energy, U effective, equal to L squared over 2mr squared minus gmm over r. That way, we can write the energy as E equals 1/2 mvr squared plus U effective. The reason this helps is because now the energy equation only depends on r and vr, which is the time derivative of r. There are no thetas anywhere anymore. So even though we live in a three-dimensional world, the motion of the particle is governed by a single variable equation. That's what makes it easy to understand graphically. Let's plot U effective as a function of r. For small r, that 1 over r squared is dominant, and it's positive. So U effective shoots up to infinity for small r. For large r, the 1 over r is dominant, and it's negative. So as r grows, the potential dives down to negative values and then rises towards 0 as r goes to infinity. So it makes a bowl shape. The exact shape of the bowl depends on L, how much angular momentum we gave the particle. And the trajectory of the particle depends on E, how much total energy we gave it. First, let's consider the case in which E is negative. The negative potential energy dominates over the positive kinetic energy. We'll plot E as a dashed horizontal line. Since the difference between E and U effective is equal to 1/2 mvr squared, which is always a positive number, the particle's radius, r, must be confined to the region where E is bigger than U effective, that is, where the dashed line is higher than the solid line, inside the bowl of the effective potential. And furthermore, at locations where E minus U effective is large, that means VR is large too, so the particle is moving quickly in the radial direction. Whenever U effective gets close to E, the particle must be slowing down. And when the lines actually cross, VR is 0, and R is momentarily standing still. All of this means that the particle's radial motion can be understood qualitatively by imagining that we drop a marble in this bowl starting at one of the intersection points. The marble starts at rest, rolls to the bottom and speeds up, rolls up to the same height on the other side, stops briefly, then drops down again and keeps oscillating. Likewise, the R value of our particle will grow, then shrink, then grow again as it's whirling around. That makes sense. We already know the particle will follow an ellipse with a distance to the origin, r, that gets bigger and smaller as it goes around. And if we happen to put the particle right at the lowest point in the bowl, it'll just stay there. That corresponds to a circular orbit with an unchanging radius. This graph can teach us other things too. For example, we've just seen that for a given angular momentum, a circular orbit has the minimum possible energy. It's the low point in the bowl. That's going to come up later in this course. Whenever you drain energy out of an orbit, with friction or some other process that leaves the angular momentum alone, the orbit will circularize. Another thing, we now see that it's impossible for the particle to ever reach r equals 0. That's because of the first term in the effective potential, L squared over 2mr squared, which makes an infinitely high barrier guarding the origin. The only exception would be if L, the angular momentum, is exactly 0. Then there's no barrier. In plain language, to make a direct hit on the origin, you need to be dropped straight in with no sideways motion. If you have any angular momentum at all, you will orbit the attractor. You won't hit it. We can also think about what happens when the total energy is positive rather than negative. In that case, the dashed line intersects the solid line only once, near the center. So what happens is that the particle approaches the origin, then turns around and flies away, slowing down, but never returning. That is an unbounded trajectory. It's like what happened in 2017, when an interstellar asteroid approached the sun at high speed and a lot of energy. It flew in from parsecs away, and its radial coordinate r shrunk to about 1/4 of an AU before the sun deflected it in a different direction and it flew away. That was an amazing event. It was the first time anyone had ever detected an asteroid from some other star system encountering our own. The asteroid was named Oumuamua, a Hawaiian word for scout. Hawaiian because it was discovered with a telescope in Maui. The plot of the effective potential tells us what's happening to the radial coordinate, but it doesn't tell us what's happening to the theta coordinate. We need to keep in mind that while r is changing, the particle is also moving in the perpendicular direction. For Oumuamua, v theta increased dramatically during that close encounter, which is why it got flicked off into a different direction. Let me show you what's happening to the theta coordinate for a bound orbit with a negative total energy. The conservation of energy tells us there will be some minimum and maximum radius for the particle set by the intersection points between the energy, the dashed line, and the effective potential, the solid curve. And the conservation of angular momentum tells us that the theta component of the velocity is L over mr. So it whirls faster when r is small and slower when it's farther out. That's Kepler's second law, which, as you might remember, holds for any central force, not just gravity. So you can play this same trick, defining an effective one-dimensional potential for any central force law, whether the force goes like 1 over r cubed, or the square root of r, or whatever. In general, what happens is the particle whirls around, going from the minimum to the maximum radius and back again in accordance with Kepler's second law. The trajectory makes a beautiful pattern that fills in the space between the minimum and the maximum distance. They're called rosette orbits. They remind me of those patterns you can make with spirograph toys that were popular when I was little. But for the special case of the inverse square law, there's a remarkable coincidence. The trajectory comes around and repeats, making an ellipse. That is a very special case. Just about any other force law, any other power of r, leads to infinitely looping rosettes, not a fixed geometric shape. In fact, there's only one other exception that I'm aware of. If the particle is attached to the origin with an ideal spring, a force proportional to r, then its trajectory is also an ellipse, but in that case, the origin is the center of the ellipse instead of the focus. Why is it that the actual force law chosen by Mother Nature is one of the exceptional cases that gives ellipses? I'm always struck by that apparent coincidence. It makes me wonder, did Mother Nature have any choice? Could a universe exist with a different force law so the planets do move on rosettes? Or would it be impossible to achieve a self-consistent set of physical laws in that case? I don't know. But I can imagine how much more difficult Kepler's and Newton's jobs would have been in such a universe. It turns out that this coincidence is related to the fact that for the specific case of the 1/r² force law, there's a third conserved quantity besides energy and angular momentum. Here's the equation for this additional constant of motion. What is this thing? We're taking the planet's velocity vector, crossing it with the angular momentum vector, dividing by gmm, and then subtracting the r hat unit vector. It looks like a bunch of random operations, like a monkey plunking on the keys of a computer running math type. This is called the eccentricity vector. If you are so inclined, I encourage you to take the time derivative of this quantity, and if you work at it long enough, you'll find it to be 0. The E vector is a constant in time, even while v and r hat are changing throughout the orbit. The magnitude of this thing turns out to be none other than the orbital eccentricity, and the direction of the vector specifies the orientation of the ellipse. It points along the major axis. In fact, working that out is one way to prove that Newton's law of gravity implies Kepler's first law, as opposed to what we did, which was to demonstrate that Kepler's laws imply an inward acceleration going like 1/r². Now, in advanced classical mechanics, we learn that whenever there is a conserved quantity, like energy or angular momentum, there is a corresponding symmetry in nature, a sense in which nature is mathematically simpler than it could have been. This is called Noether's theorem, after Emmy Noether, who published it in 1918. For example, energy is conserved because the laws of physics don't change with time. F equals ma, forever and always. What we say is that the equations have time translational symmetry. Angular momentum is conserved whenever the situation has rotational symmetry, when things only depend on r but not theta. So, what about this third conserved quantity, the eccentricity vector? What's the corresponding symmetry? It's very subtle and weird. It turns out the equations governing the motion of a particle under the force of gravity from another particle are mathematically equivalent, through a complicated change of variables, to the equations for a particle moving freely without any force on the surface of a four-dimensional sphere. And it's the perfect symmetry of that four-dimensional sphere that leads to the conservation law for the eccentricity vector. Now, if you ask me, why does gravity have this unexpected, deep mathematical property? I confess, I don't know. I'm not sure anybody does. Okay, back to the planets. Let's reflect on what we've achieved. This was a technical lecture, so it would be easy to get lost in the details. We've seen firsthand how the inverse square law of gravity explains that big physics demonstration in the sky, the motion of the planets. Achieving this understanding was a pivotal development in human history. It was our first real awareness of one of the four fundamental forces of nature. And it's also a beautiful connection between mathematics, geometry, and physics. We also derived expressions for the energy and angular momentum of a particle in a gravitational orbit, and those will be useful from time to time. We learned a graphical way to understand orbits based on the effective potential. It's a way to reduce an intrinsically 3D problem to a single variable equation. And if, in some cataclysm, our civilization is destroyed and all our scientific knowledge is lost, then you will be able to play the role of Isaac Newton and lead your band of survivors into a new scientific revolution. But for now, just enjoy a job well done and take the rest of the day off.